Today's lesson is not difficult. There requires no checking. There requires no graphing. Even though it says solve by graphing, these require no checking and no graphing. I will show you why they work by graphing, but it does not require us to do so. So we are still in Unit 5. We are doing systems. We are still doing systems of linear equations, but I don't feel like writing of linear equations because I don't want to. You can if you want. Day 3, day 4, day 7.
3.
Maddie, you don't know. Maddie's just like, yeah, day 3. Day 3. Okay. Maddie, did you actually know, or were you just saying what I wanted to hear?
I actually knew.
Maddie, you're so amazing. I know this is going to go back a little bit, but on the first day of systems, I told you there were 3 types of solutions. And all of these markers are cruddy. Can we see that? Kind of. Man, I really wish I had a really nice camera. I do. Really nice one that actually let me video the whole board rather than having to move my phone. You know what I mean, Miss Armstrong?
I do know what you mean. I've heard you say that before.
Okay, I like to reiterate it every so often. Okay. So 3 types of solution. The first solution. We have one solution. These are all of the problems that we've already done. Every single problem that we have solved by graphing has had one solution. How do we know that it only has one solution? What tells me once we graph it that it has one solution?
They only intersect one time.
What intersects one time? Because you're right.
The equation.
Good. When graphed, the equations intersect. Bless you. And I'm going to throw in this word exactly. Because, just trust me. Exactly once. That means it can only intersect one time. And we know our solution then is an ordered pair of x, comma y. Okay? We've done this. You have graphed them even after the first couple rough days, because we did have a couple rough days. I mean, we did. I feel 100% confident that tomorrow on your quiz, you're going to be able to graph and rock this. Okay? That goes for everybody in here, including new people. I have the utmost confidence that you're going to rock it, not naming names for our new people, Seth. No pressure. Okay? Now we're going to get to some of the funnier ways. And funnier, not haha, but they're not going to be one solution. So now we've got infinite. Yeah. Okay. Infinitely many solutions. And I told you, you will not have to graph them. You will not have to check them. For it to be infinitely many solutions, the equations. So when I say the equations, I mean our equations in slope-intercept form, right? Because we're not graphing unless it's in slope-intercept form. Does everybody understand that? I would hope so. I mean, we've talked a lot about slope-intercept form. The equations are exactly what? What do you think they're going to be for there to be infinitely many solutions? The equations are going to be what? Maddie, impress me, honey.
Infinite?
That was not correct. We're going to come back to you. We're going to get to that word next. Good thinking. It's not going to be parallel. We're going to say exactly the, and it starts with an S. Maddie, make up for it.
Same.
Same. Now, I don't want to tell you why yet. I want you to think about this after you write it down. Okay? So, I'm telling you that there's infinitely many solutions. We can't just say one solution and it's right. There is so many solutions that will work. Why is it infinitely many solutions if both of the equations are the same? What would happen if we graphed the same equation?
Lines being parallel, so it just keep going.
They wouldn't be parallel. David?
They're like always intersecting.
What do you mean they're always intersecting?
Like they're on top of each other, so.
Oh, wait, so if it's the same exact line. So if I graph this line, let's say it's y equals x. And then I graph another line that says y equals x. They're on top of each other. So they're intersecting, like David said, at every single point. So if the equations are the same, and I'm going to graph this, y equals x. Okay? So here we go. So here's my 1, 1, 1, 1. So it starts off my origin, up 1, over 1. Okay? There's the red one. That will be red. Here's the green one. Origin, up 1, over 1. Notice how the green and the red line are on top of each other. That means every single place where that line is, it will be a solution. That's how we get infinitely many solutions. Okay, Maddie, does that make sense? I'm glad you came back up to it. Haley, do you understand why it's not parallel? Now, let's go back to that word. I know that I've taught it in 7th grade. I don't think I've talked about parallel yet this year for us. I don't know. Teaching 7th and 8th grade, I get confused. I talk about a lot of things. Sometimes it's not even school related. Sometimes I just start talking, and I don't even know what I'm saying, and my mouth is just like spewing out stuff. Does that happen every so often? Yeah? Okay. Only once or twice. Jackson, what was that word that you told me that started with a P? Parallel.
Yes.
Sometimes don't give me that look, Brooklyn. Huh?
There's no like.
Okay, then don't stare at me, Brooklyn. Winning. Mr. H is winning. Parallel. The pure geometric definition. Two lines in the same plane. And that's important in geometry, but in the same plane that never intersect. So if they never intersect, give me some examples in this room of two parallel lines. Look around this room. Give me some examples of parallel lines in this room that never intersect. Matt.
The two long sides of that door.
Yeah, the door frame. So the edges of the door frame. If our door is wonky, it's not going to close. So these edges of the door frame. Keep looking around. David or Jackson. Yeah, the frame of the chalkboard. Well, let's use the whiteboard because here, or the top and the bottom. What else? Go ahead.
Ceiling.
The things that hold the ceiling tiles. Okay? Go ahead. The window frames, right? The silver parts of the window frame. We could do this a long time. The edges of the blocks, right? We could keep on going. There's a lot of things in our everyday life that are parallel, that never intersect. So, with the word parallel, we can now go to no solution. It didn't start off green. No solution. No solution. this is important. The equations have the same slope. Give me a letter that we can abbreviate slope for. Alyssa.
M.
M. The equations have the same slope, M, but different y-intercepts. So the key is they have the same slope but different y-intercepts. Hey, B, can you give me an abbreviation or a letter variable for y-intercepts, B?
B.
No, I'm asking you. Who's on first? It is B, B. Good. Not BB, but just B. You're B. That's B. Okay? So the equations have the same slope but different y-intercepts. Why? They're parallel. If they have the same slope but different y-intercepts, that means the rise, the change, the rate of change of that line are the same. They'll never intersect. If they never intersect, can they have a solution? Well, clearly not. That's why I wrote no solution. So you will not, don't graph. Don't graph those. If you see them, don't waste your time. If the equations are the same, don't worry about it. Just put infinitely many solutions. Okay? You cannot use the words all real numbers for this because that's not true. It's infinitely many solutions. You need to know this phrase. You need to know no solution. Putting 0 is not the same as putting no solution. So we have 3 different types of answers. One solution. You've proven over and over and over. I said I only wanted to spend 3 days on this. I think we've spent like 8. Or at least it seems like it. That's all right. Do you understand how to graph? Do you understand how to find a solution now? You know how to find one solution. If they're the same equations, you could graph them, but it's only going to look like one line. They're infinitely many solutions. If the slopes are the same. So if I give you y equals 3x plus 6, y equals 3x minus 12. Do not graph it. Why not? My m's, my slopes are the same. But what's different? The y-intercepts. Because if the y-intercepts aren't different, then it's infinitely many because the equations are the same. Questions, concerns, problems. So you will have to graph for one solution. You should even check for one solution. Then you're going to get some infinitely many solutions where they're the same exact equation. You can graph it, but you're going to get the same line. You could graph no solution, but then you're going to raise your hand and be like, Mr. H, they don't intersect. And I'm going to go, I know. Like, hooray, we're done. Happy Tuesday. Quiz tomorrow.